All right, thank you so much for joining us. Have some good news and bad news. Bad news, getting paged at 3 a.m., going through your alert storms, troubleshooting 5 hours for a 5-minute fix, it's not going to go away. But the good news is that if you can build an intelligent system that can correlate the telemetry signals, that can help us make the decisions faster. And that's where we believe AIOps can help us. And that's going to be the focus of today's session. My name is Vikram Venkataraman. I'm a solutions architect at AWS. I work with some of our strategic customers that operate Kubernetes at large scale. Any platform engineers, SREs in the house? You have my respect, folks. Well, OK, let me ask this question as well. How many of you here operate more than 50 Kubernetes clusters? Keep your hands raised if you're operating more than 100, 500, 1,000. OK, not a lot of you, but I hope we can take some of what you learned today, convince an org, and do this POC on the AIOps framework and help manage Kubernetes in an intelligent way, I would say. That said, I'm a big fan of analogies. I wanted to emphasize on the challenges and the nightmare of managing Kubernetes clusters at large scale. So I came up with this, the Interstate 75. Now, if the data is correct, the Interstate 75 is the 3rd busiest interstate in the whole of the United States. Imagine putting yourself sitting at the traffic control center. You would want to make sure the traffic flows smooth. There is constant movement of vehicles in and out of the city. There is crashes, weather inclements, you name it. You got all the challenges. Sounds challenging, right? Just multiply this chaos by 10 more interstates, and that's exactly what we mean when we say managing 1,000 Kubernetes clusters feels like. A disclaimer, this is, yes, a session on AI, but the slides are not generated by AI, except for these images. But that said, it's all generated by myself. Now, looking from the lens of an on-call engineer who wakes up at 3 a.m., and he finds there are 10,000 alerts waiting to be attended. Probably he may have to go through 50,000 time series of metrics, 2 petabytes of logs, and he's already racing against the time. Do you think this is a monitoring challenge? No, it's an intelligent crisis, right? The lack of correlating the telemetry signals, and where a 5-minute fix takes 5 hours for you to troubleshoot, that tells us there is fundamentally wrong in the way we operate, right? Now, these are some of the reasons where the on-call engineers has to firefight. These are the major hurdles he's going to face. First thing is isolating the noise from the actual information or the actual problem, right? Because I said there are 10,000 alerts. He has to spam through them and identify the one that matters the most. Getting to have all the information that flows across your complex architecture. Because many a times, it's not that application. It's some dependent application that is causing the actual outage. So you must have all the information as your request flows through your complex architecture. Third, we all have varieties of monitoring tools in our environment. We have Prometheus for metrics, logs and traces, Elastic, you name it, all sort of sophisticated tools. So he or she, the on-call engineer, should log into these tools and get the insights. And that's going to take a lot of time. And that's where we see engineers facing the increase in mean time to identify any issues. That's where they spend most of their time. And let's say they identify the problem. They go to the root cause of the problem. The next thing is applying the fix. Many a times, it's not the one who developed the application that's going to apply the fix. It's the on-call engineer, poor on-call engineers, or the platform owners, right? So the lack of runbooks is going to further increase the mean time to remediate any operational issues. Long story short, it's the intelligent crisis, the inability to swim across ocean of telemetry signals. That is the biggest problem when it comes to managing the operations of the Kubernetes cluster. And that's where AIOps can help us. Now, AIOps, people say this is a new buzzword, but it is not, right? We've been doing AIOps for quite some time in the name of anomaly detection. Who here does anomaly detection? Quite a few of you, right? Predictive auto-scaling. Intelligent automation, where a simple script that you run kind of fixes a problem, right? These are examples of earlier versions of AIOps, But there is a huge difference between those traditional tools and how AIOps work. The difference lies in the fact that the AIOps tool that is powered by the LLM gives you the ability to correlate the signals, whereas the traditional signals or the traditional tools lack that. So a robust AIOps solution or a framework can help you identify the problem, can tell what really happened, what was the root cause of the problem, how can you fix that, and how can you remediate that, finally prevent that issue from happening in the future. Now that we know a good understanding of what AIOps is, the fundamental component, the block of the AIOps framework is agents. What are agents? Now, I mean, pretty sure everyone here is like quite familiar and may have a lot of agents running in your environment. But put in a simple terms, agents have specific goals, right? Now, this is where you spend most of your time giving the context to the agent, like telling, hey, you are a Kubernetes operations assistant. You go through metrics, logs, traces, identify the root cause, and possibly provide a remediation, right? The more information you provide, the agent can be prevented from hallucinating or at least getting like deterministic output from the agent. You also provide the evaluation logic within the agent, like whenever you're prompted for some kind of a troubleshooting, just go through your audit logs to see like nothing has changed in the recent, or try to see if the issues on the application side or the infrastructure side, or try to find out if this is a dependency-related issue, right? All those kind of evaluation logic is going to take you a long way. Agent also has access to tools. Just like how humans would interact with the backend telemetry signal platform, the agents has necessary tools to run kubectl commands on your cluster, run PromQL queries on your Prometheus time series database and whatnot, right? So the agents also has the tools that it requires to get insights from the telemetry platform. And the agents also has memory, both long-term and short-term. Short-term because it has to preserve the context and provide the response appropriately, right? It should understand like the problem is about troubleshooting a spike in the CPU, a downtime, a particular application being down. So it has to preserve the context. And finally, the long-term memory because it has to also preserve the user preferences. For example, a SRE engineer will totally expect a different response than a business intelligence person, right? So the agent has to kind of understand who the end user is and provide the responses in an appropriate way. Finally, the agent also perform actions against your environment. Now, this is where you do things like increasing the size of the pod, restarting a deployment, rolling back a particular version of deployment. So all these are tangible actions that can be performed on your Kubernetes environment, and each of these components have a tight observation loop. Now, this is where you observe your agent. You make sure that the agent responds in a way that you would expect it to do so. And if there are like derailments, you kind of try to correct them. Now, once we have a successful agent build, what is the biggest challenge that we come across? We're not going to stop with one agent, do we? Definitely not, right? We will spin up hundreds of agents, and your agentic solution is as successful as your agentic framework. You should have, just like how you have a Kubernetes orchestration platform to manage your hundreds of thousands of microservices, you definitely need a good agentic framework to run agents at scale. Now, this is where we talk about how different agents should communicate between themselves. How do you configure the runtime of the agents? How do you make sure that you provide the right knowledge base to these agents so that they can not hallucinate and provide the responses that you're looking for? And setting up the guardrails, what level of permissions do these agents must have? All those informations are integrated within your framework, and this is going to be critical for any successful agentic solutions. Now, I was working with Srikanth, who manages 1,000+ Kubernetes clusters. So when I was collaborating with him, we found out that most of the time, his engineers spend time identifying where the issue was. The mean time to identify the issue was significantly high. So we wanted to come up with a prototype. We took a simple EKS cluster. We wanted to resemble their architecture as much as possible. So we deployed a bunch of components, KHGPT operator. Anyone here aware of what a KHGPT does? Perfect. Yep, we do have a KHGPT operator, an Argo CD controller. And for storing the metrics, we went with Prometheus. Now, we built this collaborator agent, which provides the UI to your engineers, right? So this is where the engineers can interact with your AIOps solution. So the so-called collaborator agent had specific instructions on how to understand the prompt and how to invoke the backend agents based on what you're asking. So the first agent was the Prometheus agent. So it basically integrates with your Prometheus backend, transforms your natural language questions to PromptQL queries, gets the insights back, right? The second agent we had was the KHGPT agent. Now this is where you get insights from your real-time logs and cube events. And these two agents form the MTTI side of the things, mean time to identify any problem. We wanted to go one step further and also wanted to remediate some of the actions. So we built an agent that integrates with Argo CD and does actions such as restarting your deployments, rolling back a version, increasing the size of the pod, and those basic actions. And all of them had like close integrations to the IAM boundary, the identity boundary. So it had a human in the loop kind of a action in place. So once you confirm, only then the actions can be performed. With that said, to put in a nutshell, it'll look like something like this. You have the collaborator agent. Let's say you want to know if there are any errors in your Kubernetes cluster. The agent kind of integrates with KHGPT, gets the response back. And if you want to get the utilization information, you have the agent talking to our Prometheus agent, getting the insights back. So it's a one-stop shop where you technically get all the insights about your Kubernetes cluster, and you can perform some basic remediations. Now I'm going to turn it over to Srikanth to talk about how they kind of evolved from this architecture, build a robust AIOps architecture, and how they are managing those 1,000+ clusters, and they have significantly reduced MTTI and MTTR. Over to you, Srikanth.
Thank you, Vikram. Am I audible? Hey. Good afternoon, everyone. So I'm Srikanth. I work at Salesforce as a Senior Director of Software Engineering. For the last 2 decades, I've been building software systems to manage infrastructure. We have been building traditional automation to keep our systems and services reliable, but there is still a big reliance on human intuition to solve problems, like be it debugging, cascading failures, or predicting outages, or simply just figuring out something that should work in production is not working anymore. Why is that? There is still a large reliance on humans. I've always been dreaming about the future where this whole infrastructure space can become fully autonomous and the machines can manage themselves. That's why I'm super excited the emergence of Gen AI and the possibilities it gives us to make progress towards building the autonomous future. In this talk, I'd like to share about our journey to implement an AI-powered self-remediation loop, a simple AI-powered self-remediation loop to solve production issues at scale on our Kubernetes fleet. Quick introduction to my team. We are the Hyperforce Kubernetes platform team. Hyperforce is the Salesforce's next generation infrastructure platforms built on the public cloud. Hyperforce powers all clouds within Salesforce, including the Sales Cloud, Service Cloud, Marketing Cloud, Commerce, Industries, even Agentforce, and more. And our team manages the compute stack within the Hyperforce layer. We are a platform engineering team. We provide Kubernetes namespace as a service to all of the internal application teams within Salesforce. We essentially abstract the lifecycle management of Kubernetes infrastructure away from all of our developer teams. We let them focus on their business logic while we handle the applications. Wide variety of applications run on us, from Java monoliths to highly transactional databases to low latency caches to streaming big data applications and more. It is a quick sneak peek at our tech stack. It's a very simplified version of our tech stack. So on top of plain Kubernetes that runs on multiple clouds, we operate a ton of components. As a platform, we are expected to provide all the standard capabilities on top of Kubernetes, things like storage, networking, auto-scaling, DNS, Istio, and mesh. In addition to that, we also provide out-of-the-box integrations to Salesforce custom infrastructure services for managing identity, security, authentication, secrets, and security management. Our secret sauce is to provide clean and easy-to-use interface via powerful platform abstractions using custom Kubernetes operators and APIs. So all of our customer teams can easily leverage and adopt our platform. In the essence, we build on top of native Kubernetes to bridge the gaps. We enforce best practices. We manage cost and complexity so that our application teams or the product teams do not have to worry about them. A quick peek at our operational scale. So we operate about 1,400 plus clusters spread across multiple clouds. We run millions of pods on our infrastructure. We run hundreds of thousands of compute nodes. We manage 40 to 50 components on top of plain Kubernetes. And we also spend a lot of time supporting this infrastructure. About thousands of hours goes into keeping this infrastructure reliable. And one of the biggest problems that we are looking to solve right now is the scale. Our platform is expected to go 5x in the next couple of years. So how do we scale our whole operations is a big challenge that we are looking up to solve in the coming years. That's where AI fits in. We are trying to leverage AI to see how it can help us solve the scaling problems. Wanted to share a quick evolution of our tools. We have a culture of developing automation and tooling, and as we scaled our platform, we built a lot of tooling. Many of them are in-house, Salesforce specific, but some of them we have open source, like Sloop. We have tons of metrics and logs, and we have built a lot of dashboards around it. We built Sloop for Kubernetes history visualization. We built Periscope for class cluster feat-wide analysis. We built KubeMagic Mirror, again, another internal tool for automating the troubleshooting workflows on Kubernetes. We built KubeMagic Timeline for correlating sequence of events across different layers of infrastructure dynamically. And we, last but not the least, we also built something called a pseudo API, which streams Kubernetes events out of production clusters onto a secure internal developer environment. And we built a pseudo Kubernetes API server that mimics the Kubernetes API. And this lets our on-call engineers and our developers directly do kubectl on a read-only data replica of on the internal environments, so without logging into production. So we have built a lot of these tools, and why is there still a problem? I think we still had gaps. These tools are pretty much siloed. They don't talk to each other. And we have to pass context manually between them. And there is still a high learning curve. All of our engineers need to know all of the tools and how to use them efficiently, when to use them. And there is and most of these tools are pretty static, and the rate at which we go and update these tools is somewhat low. And the feedback loop, we don't have a good feedback loop mechanism for these tools yet. So all of this put together, there is still high toil for supporting the infrastructure as a whole. That's where we felt there is a huge opportunity with AI agents coming in. Like, can we use it to improve our MTTR? Can we use it to reduce our human toil significantly? So we started exploring with agents. We didn't go big bang. At the beginning, our journey was small. We started exploring agents by building agents for solving smaller use cases. Our first agent was an on-call report agent, which basically looks at previous weeks of on-calls work, comes up with a report and summary of the alerts, and what percentage were remediated, how long it took, and what happened during the previous week. And this was an instant hit. Like, all of our engineers loved it. They adopted it quickly. Now the on-calls don't have to do this work manually, so it gets done for them. And it's 90% of the work, what they do is automated. They just add some details. We also built a kubectl agent. Like, we know that we built the pseudo API. We can do kubectl on our dev environments. But do we need to learn the syntax? Like, can we make it more easier and integrate with Slack? So we built an agent that integrates with Slack, that translates the natural language questions to kubectl commands, and it executes on our pseudo API. And not just us, even our customers leverage this today. And slowly we increase the scope. Every week we analyze the availability and the other golden signals across this fleet of 1,400 clusters and the 50 components that we run on top of them. This is a huge problem where we have to detect all the anomalies and then root cause and figure out why those anomalies happened, and then come up with the analysis data, and basically come up with the action items to solve these problems. This was taking at least a couple of days every week for engineers to do this manually. So we built an agent that automates this anomaly detection, goes through all of these clusters, goes through these metrics, comes back with a set of clusters which have the problems, and then do the first level triage or analysis of the problems, and gives us an auto-generated summary of what happened the last week. So this was we started doing this. The engineers quickly adopted it, and this does about 80% of the work that engineers need to do on a weekly basis to review the life site work. So here is a quick snapshot of our on-call report agent. So on Slack, engineer can generate the on-call report for this time frame, and the report is generated, and there is a doc that gets generated and is shared with the engineers. It is another snapshot of a kubectl agent, wherein engineer is asking, hey, get me the events from this namespace, and filter out the events for these specific pods. And he also says, get me the events from the cluster, just don't show the commands. So it's able to get those events, and it's able to show the events, and it's all dynamically done. With that, after a lot of experiments, we kind of landed on this multi-agent architecture for implementing our self-remediation loop. We heavily rely on our internal managed agentic runtime and the embedded RAG system to power this. The agentic framework actually handles the governance piece, ensuring data security and data privacy. It is very critical, given that we are dealing with sensitive logs and metrics that can come from the telemetry systems. Fortunately for us, it was handled by another platform team, so we just leveraged that. Now let's talk about the remediation loop itself. How does it work? It all starts with the alerts. The alerts land on Slack. Slack is where we track all the troubleshooting progress, and the engineers collaborate on it. So once the alerts land in Slack, the manager agent actually kicks in. It basically looks at the alert, and its job is to come back and figure out the right troubleshooting steps for troubleshooting this problem. And it does this using the knowledge that we ingested into the RAG system from our runbooks, and by leveraging the power of LLMs. So once the manager agent comes up with the troubleshooting plan, it then needs to look across the telemetry data from the logs, metrics, events, and traces to correlate and then and identify the root cause. And it does not do all of that by itself. It delegates the task to a set of worker agents. These worker agents are trained to integrate with all of the data systems and other infrastructure tools that we have within Salesforce. So we intentionally want to leverage all of the existing tools that I talked about earlier. So we trained these agents to integrate with all of our existing tools as well. So and these our MCP adoption has been somewhat slow. Some of the systems have MCP, so wherever there is MCP available, these agents talk MCP, talk to those systems through MCP. Wherever it's not available, it's a direct integration with them. So once the worker agents gets all of the data, it passes them back to the manager agent. Manager agent again uses the runbook and the LLMs to correlate and synthesize this data and come up with the probable root cause for a given alert or for a given problem. And it passes that information to the remediation agent. So the job of the remediation agent is to identify the right course of action to solve the problem. It could be pod restart, could be node restart, could be changing some configs. And it actually does the action through something called as safe operations. I'll talk about safe operations in a bit. And we had established a human-in-the-loop review process, at least in the very beginning, for every action that AI is taking. For some time, we want human approval that's embedded in Slack. And once we gain confidence that AI is able to take the action, we grant it more autonomy. We let it go. We take the approvals out of place. So essentially, with this architecture, it allowed us to leverage all of our existing tools and runbooks. And while building an agentic layer on top that can meaningfully orchestrate all available tools and can do the troubleshooting much faster. At least what we found was the initial analysis after the alerts come in is much faster now. It's automatically triaged, and we have the initial analysis done much faster. Moving on, let's talk a little bit about the safety risks with AI operations and how we can mitigate them. As we implemented this solution, the biggest question that we had in mind was, how can we make this safe? How can we trust AI to make any kind of operations, especially in a production system? So there are 4 things that we found that we wanted to fix. Starting with unbounded access. We don't want to give AI all or the God access, so it can go and make decisions and can create disasters. Like, it can actually delete your control plane, it can delete your node pool, it can delete your config map and whatnots. So we restricted AI actions to a limited, curated set of operations that we thought was something that AI could operate on. Number 2, guardrails. Like, every single operation, and if you use raw tools like kubectl or SDKs, they lack the necessary operational guardrails to ensure safety. So we implemented safeguards for every single operation, and wherever possible, we ensured that these operations are rollbackable. Poor visibility, without tracking what AI is doing, it increases the risk. We don't know what it's doing, whether it's doing right or wrong. So we established strong auditing and strong change management around every action that AI is taking, and it's very closely monitored, and we have dashboards and visibility around it. And lastly, we still needed human in-the-loop oversight, at least in the beginning, for every new operation that we automate. Humans validate it first for some time, we gain confidence, and then we grant autonomy to the AI. So how we actually implemented all of this, this is our architecture. So we implemented all of them as Argo workflows, and they're exposed via our in-house compute API. AI agents can access this compute API and can execute these workflows with human approvals now, and we intend to remove them later. And they are tracked via dashboards. So let's talk briefly about guardrails. Like, what are the guardrails that we can put? So if we take an operation like a pod restart, are you respecting PDBs? If you just go and do a kubectl delete, it's not. So you don't know. It can cause issues with application partially, or sometimes even a complete application outage. If you're restarting nodes, how many nodes are you restarting in a given period of time? Like, if you restart too many nodes, you lose capacity, and that can create issues. Are you scaling up or down? Are you looking at the cluster utilization themselves? Like, we have had a couple of incidents where there was like a 2,000 node cluster, and we scaled it down to 1,200 by accident, and there's like a massive outage. It was a human error at that point in time. But these kind of things can happen. So what we did was we looked at every single operation that we wanted AI to do. We worked with our seasoned engineers, what actions they take to make these operations safe, and we kind of coded them into every single operation. So the combination of safe operations and restricted access to AI and all the guardrails, it kind of gave us confidence that we can allow AI to do certain operations and grant them autonomy over a period of time. With that, OK, here is a quick screenshot of our remediation approvals. This was a problem. There was some problem with the disk on a node. AI figured out, the agents figured out, hey, this node has some issues. I have to drain the pods. And it's asking confirmation from the on-call engineer. Hey, do you want to drain this node? On-call engineer can look at the entire history of the diagnosis, the RCA, and then if he decides, yes, we can go ahead and do it, there is a button to click. It doesn't immediately execute. We also implemented a secondary guardrail where this goes to another peer engineer or manager who has to approve this, and then we execute this. And as we gain confidence, we can remove this remediation loop, at least for specific actions one by one. So what is the impact so far? Again, we are in very early stages. We have automated only very few. We have automated only very few operations. So far, it is saving us about 150 hours of human toil every month. It is roughly an engineer's worth of time that we could use to scale our platform. And we have seen our average troubleshooting time improve by 30%. Overall. This impact could be a lot more if we had good coverage. We had to build operations. We had to have coverage for all of our alerts, which we don't have at this point. We are still working towards it. So what are some of the learnings that we had from this implementation so far? Your runbook structure and accuracy is key. As soon as we put this live, we figured out that we had duplicated runbooks, which had conflicting data, outdated data, and that creates a lot of issues. In fact, we had to go back and change our runbook structure to make this whole solution work. So data accuracy is key. AI is only as good as the data that we provided. It required a lot of extra work to build safe operations, but it was needed to make this safe. And we needed to ensure continuous feedback loops. We need to actually make our prompts. We need to add additional guardrails to prompts as well. Make sure it is grounding all of the decisions to be backed by data. And in general, we felt that leveraging existing tools was more powerful as well. So we get faster throughput by leveraging our existing tools. And also, Slack-based user experience is proved to be really great. We are able to capture all of the knowledge, all of the discussions that's happening in Slack, and then immediately feed it as the knowledge for future improvements. Again, we think this is just the beginning. This is not the end. We have just scratched the surface of what AI can do. It can do a lot more. One of the biggest problems that we see today is this solution. With this solution, with the runbooks, we're not able to connect the dots meaningfully still yet. So if you take a complex problem where an application is experiencing latency because its DNS calls are timing out, and the DNS itself is running on another node that is experiencing network exhaustion because some other part is hogging the traffic. How do you connect this application to a core DNS problem, to a node problem, to a network interface problem, and tie it to another part? It is very difficult to write a runbook. Even if you write a runbook, it is very static for one given case. How do you do it across all the cases you see with infrastructure? So we are attempting to actually teach AI how we would teach an engineer about the infrastructure, like laying out the infrastructure landscape. These are the components. This is how they are connected. These are the failure types that we see with these components. And if it fails, this is how the impact might look like. So we're trying to build a knowledge graph that mimics, that has all of this information as part of it. And we want to let AI traverse that knowledge graph every single time to go and connect the dots from through all of the phases of, or through various parts of the infrastructure to exactly find the root cause. We could also do better with our memory. We only track them with our Slack-based feedback loops today, where we don't feed it back to AI in a way that it could reuse it. So we thought with the knowledge graphs, we could do more by implementing something like a confidence score, and so that AI can make better decisions with the memory it has about past successes and failures. And beyond that, we are also curious to know more about how to use AI to detect and troubleshoot the hard performance problems which even humans struggle today. There's so much metrics, so much data that's available. How can we use AI to synthesize, curate, and figure out the right set of problems, something we don't have an answer, that we are curious and we want to research more. Hopefully, by doing all of this, we could scale our AI agents to eliminate 80% of our toil, which is our goal. With that, thank you, everyone.